All right, so section 4, chapter 9, we are going to develop some new techniques, some new tests, but we still have our sights set around two of the two of the basic goals that we've been dealing with all along. Does a series converge or diverge? And if it does converge, what does it converge to? Okay, so both questions are would be considered a victory to be able to answer both questions, but or either or. Now, what we want to be able to do is we want to have some techniques in our pocket where even if we can't answer the second question, what does it converge to? But we still have the techniques to be able to say whether some series converges or diverges. Okay, so remember, we're talking infinite summation. If you have an infinite sum, does it converge or does it diverge? And we're going to talk about a couple tests. So the first test, both of the tests in this section are what we call comparison tests. Okay, and the first type of comparison test is a direct comparison test. And by direct, what we mean is we're going to compare the terms of two different series directly. And this is the game that's going to be played. So I'm going to give you a series that is going to very much resemble a type of series that you have encountered before, and one that you already know whether it converges or diverges, particularly geometric or p-series. But the question then becomes, well, although we know that this other series converges or diverges, what can we then say about the series that is asked of us? So I'll get into a little bit more what I mean by term, but let's start with the theorem, and the theorem is very important, and do not skip over this, or if you do, you're going to start to say silly things, okay? So notice the way it begins. So we have a sub n and b sub n, and it's basically what we have is we say, well, let a sub n, the general term a sub n, nth term, be greater than 0 and be less than b sub n, which is another nth term, for all n. With me? So this a sub n, that is going to be the given series that you want to compare. The b sub n is going to be the series that resembles a sub n. Now let's assume all of that we have found out through investigation, or that all of the above has been met. Now, what do we get to say? Well, I'm going to read this to you in other words in just a second, but this is the if-then statements that we get to make if the following is known. Ready? So the first one, we can read that as if the larger series converges, right? Because b sub n would be the larger series. It's always greater than or equal to a sub n. So if the larger series converges, then the smaller series converges, right? That is what number 1 is stating. If the larger series converges, then the smaller series converges. We also can say that if the smaller series diverges, then the smaller I just wrote smaller twice. Let me fix that. So if the larger series converges, then the smaller series diverges. And now let me rewrite 2. That would be a tautology. If the smaller series diverges, then the smaller series diverges. All right. So let me replace that with larger. So let's try that again. So if the smaller series diverges, then the larger series diverges. Okay, now, since there was that error, I'll just reread it quickly. So notice what you can say. If the larger series converges, then the smaller series converges. If the smaller series diverges, then the larger series diverges. There you go. That is the direct comparison test. Now let's spend a second to make sure you understand what the theorem does not say. What does it not say? Well, if the larger series diverges, nothing, right? If we have, we get to make a statement if the larger series converges. We'll get to make a statement about the smaller series. But if the larger series diverges, what do we get to say? We get to say nothing. Nothing from the direct comparison test, at least. What else does this theorem not say? If the smaller series converges, then we have nothing to say about the larger series. Again, if the smaller series diverges, we do get to make a statement about the larger series diverging. But if the smaller series converges, we are stuck. We need a new method. The direct comparison test does not work. Okay. Now, I want you to keep in mind what the limits of the test. Okay, the test has certain limits that we can apply, and these are the statements that we can make. Let's go ahead and begin. So we're asked, determine the convergence or divergence of the following. Now, you're going to have a playbook, an entire playbook of various tests that you can pull from. And often there are many tests. You can use multiple tests to make the same statement about convergence or divergence. But as of right now, we don't have a test in our pocket that allows us to make a statement about convergence or divergence. So we're going to use this direct comparison test. Now, let's go ahead and let's do some step-by-steps. How's that? So first, I want you to recognize what has been given to you. This 1 over 2 plus 3 to the n, that is the a sub n, right? That is the series that you are given that you want to compare. Now, b sub n is what you are going to have to come up with, so that resembles a sub n. All right, and by resembling, I mean we want at least to be to the same degree as a sub n. So if we have 2 plus 3 to the n, then we want something 3 to the n, okay? So let me go ahead and get us started on b sub n. Now, one of the series that resembles a sub n, and one that we already know the conclusion, is the following. Okay, so this, if you have watched the previous videos, hopefully you would be able to recognize that this is a geometric series. Okay, and remember, a geometric series can be rewritten as A, R, I'm going to write that A as a capital A, okay, so we don't confuse it with A sub n. So geometric series can be written as A, R to the n. And I've already explained this to you, how you can go from here to the power of n. So this would be a scenario where we have 1/3 to the power of n. Okay, again, if you have to go back to the previous video to make sure you understand why, you will have to do that on your own time. So, okay, so in this case, r is equal to 1/3. We don't need to know what a is right now because we can automatically make a statement about this series based on r. So remember what we can say. Remember with geometric series. So if r is between -1 and +1, then the series what? Then the series converges. Okay, so what do we know right now? So let's go ahead and I'm going to come off to the left. So I know my a sub n, which was given to me. And I'm going to kind of go down to the bottom here so I can give myself a little bit of room. So I know a sub n is equal to 1/2 plus 3 to the n. And I know that in this case b sub n is going to be the geometric series 1/3 to the n. All right. And now, what I want to do is, if you want to do a direct comparison test, let me go ahead and tell you really quickly. I'm going to erase this as soon as I write it. I want to be able to make a statement about, is this greater than, less than, equal to, which we know it's not going to be, but you understand, I want to be able to make a statement about which is the larger series. So let us go ahead and stop for just a second. Let's go back to the previous page because we have chosen 1/3 to the n, which converges. So we need to be able to make, if we want to be able to make a statement about a sub n, let's figure out what it is that we can, the types of statements that we can make. Well, in terms of converging, the larger series, if the larger series converges, then the smaller series converges. So this is only going to be useful to us if this is the larger series. Okay? So we want to be able to make a statement that this is the larger series. And now we're going to use the term-by-term comparison to do that. Ready? So we're just simply going to let n equal 1. All right, and then n equal 2, n equal 3, and we're going to do the same thing here. N equals 1, n equals 2, n equals 3, and it's that simple. We're simply going to plug in. Now, the better way, obviously, to do this would to be able to use n and n plus 1. Okay, but what I want to show you, I just want to show you for this one how we're just going to be able to plug in 1, 2, 3 for both of these series. Let's start with 1. So if we plug in 1, this would be 1/2 plus 3 to the power of 1. So that would be 3 to the power of 1, so that would be 1/5. Let's come over here. If we plug in 1, this would be 1/3 to the 1, which is 1/3. So far, a third is more than a fifth. All right, if you got to turn them to decimals, you'll have to do that. We could continue. All right, we'll go ahead and continue. So if n is 2, this would be, we've got 1/2 plus 3 to the power of 2. So I think that's going to be 1/11. Right, and I know this over here will be 1/9. Oh, I think so. I'll just confirm that really quickly. I'm pretty fairly positive that's correct. Okay. And And then again, once again, 1/9 is larger than 1/11. Let's see here. If we do n to the power of 3, that would be 1, what do we got? 1/27th. And now this should just be 2 more than that, so that should be 1/29th. Okay, and again, 1/27th is larger. So I get to be able to make a statement as of right now that B sub n is the larger series, right? You'll agree with me that each of the terms, and I've only listed 3, so you can see how this is incomplete. Now let's go back to our comparison test. So what do we get to say? So all I want you to know right now is that our B sub n is the larger series. So, and we know that the larger series converges because we chose it. So if the larger series converges, then the smaller series converges. So by direct comparison test, which is important for you to make a statement about how, so by theorem 9.12, the direct comparison test, we get to make a statement that A sub n converges. All right, so if the larger series converges, then the smaller series converges. All right, so therefore the A sub n also converges.